Hello, let's continue our advanced Sudoku series with Hairdo by Sam Cappleman-Lynes. So this is puzzle number 6 of chapter 3 of the Sudokult Gospel document, which you can find in the description. You can also find a link to the puzzle in the description if you want to try it yourself. I know what technique I'm looking for and how it works, but I do not know where to find it in this puzzle, and I'm going to get started right now. This is like super suspicious though. I think we could just do some normal scanning first, just to get as much as we can, because seeding the puzzle for the end is always good anyway. These threes look into here, so it's a 3 and 1 of these two. 1, 2, 3, 4. Wow. What should I do here? I'm getting distracted by by how this looks. 4s look into here. So 4s in one of these two. I'm not seeing anything else, though I might be getting distracted. Let's see. Down here we have 2 4s and this 4, so 4s in one of these two. 2 5s. Puts a 5 in one of these two. 2 1s. This one puts a 1 in one of these two. 6s, no. So 4s, 1s, 5s. Okay, how about down here? We do have a bunch of 5s already. 8, no, 9. We've got a singular 7, a singular 8, and a singular 9, so we're not going to get much out of those. We got 2 6s, a bunch of 1s, 3s, 2s. Okay. Vertically, we've got these 2s. No 2 over here. We do have 2 4s looking down, so 4s in one of those two. We have 2 5s looking up, so 5s in one of these two. Over here, we've got 2 1s looking up, and one's not there, so one's one of these two. 2, 3, 4, 2 5s look up, but there's not another 5 up here. I don't really want to mark 5s here, so we'll hold off on that. Normally I'd look for something looking into here, but they're completely empty houses, so that's not helpful. Over here, the 3s look down, putting a 3 in one of these two. And I think we've seeded with what we can. Okay, so let's pay attention to what these are actually doing then. Let's look at where 1s can be. And what I'm going to do is I'm just going to literally highlight everywhere a 1 can be. So we'll start with these. These are green. So we know 1s are limited over here. We know 1s are limited to one of these two, actually. So let's put 1s there. 1s in one of these two, so we'll put 1s there. And 1s are in one of these two, so we'll put 1s here. Is there another digit that does that? Did I miss that? I'm not sure that I did. We do have 4, 5, 2. We do have 2s here, so let's split. Oh no, 2s in the box already. All right, so did I catch every box? Okay, so 1s are just this box. This box. I just didn't color it. Okay. I don't think this pattern does anything. I think this is just 1s want to get resolved. Once you get one of these 1s, it resolves all of them. So yeah, okay. So nothing with 1s. Let's just get rid of the green there. Let's look at 2s then. We'll just keep using green. So 2 was in one of these two. 2's over here. 2's in any of these. In this box, 2 is literally anywhere. There's no 2's over here. So 2 could be in any of the, not on the top. And then 2's in this sort of quad here. I do not see anything to do with 2s, unless I messed something up. Okay. Could it be the singular 8, 7, 8, and 9? You know, I suspect, yes, yeah, actually. Let's skip straight to 7. So 7 can be, the point is 7 can't be here or here. That's the point. So 7, let's just look at these 4 columns. This is where 7 can be in these 4 columns. Column 3, column 4, column 5, and column 7. Green is where 7 can be because these are all just filled with non-7, right? And so this forms what's called a jellyfish. A jellyfish, remember our X-wing and our swordfish, we can just extend that. So in these 4 columns, green is where 7 can be. And that is that's 4 columns. And they completely line up in 4 rows. In this case, row 1, row 6, row 8, and row 9. So in these 4 rows, because it's 4 columns that can be covered by 4 rows, that means that we cannot put any 7s outside of green in those 4 rows. These aren't allowed to be 7. So for example, if I were to put a 7 here, what happens? Well, now none of these can be 7. They aren't green anymore. And so now I need to put 4 7s, because 4 columns needs 4 7s. I need to put 4 7s in green. Try to do it, right? You can't. And the reason I can prove you can't is there are only 3 rows involved, and 3 rows only get 3 7s. So I've broken the puzzle by putting a 7 there. So to use the more technical description that we did before, that's kind of extensible, is purple. Purple is our base set. Our base set are these 4 columns. And our cover set, I'm just gonna do all this. Our cover set is blue. And I'm just gonna leave the green. Green is in both blue and purple, right? Blue is our cover set. Blue completely covers 4 rows, can completely cover the green cells that were given by the base sets of purple. So purple needs 4 7s, and those 4 7s can be completely covered by blue. And so the rest of blue that isn't in green may not be 7, or there won't be enough 7s to go around. So all of blue is no longer a 7. So I think I just have to pencil that these are non-7. So let's do that, I guess. Let's get rid of the ones that aren't interesting as not 7. So I'm going to get rid of all of this. And then these already, I'm going to get rid of the givens. And then these already couldn't be 7. So the remaining blue cells can't be 7. Now, is there something obvious I can do about that? Or do I just need to pencil them? All right, so this can't be 1, 2, 3, 4, or 5. So it's 6, 8, 9. So it can't be 7 anymore. So we'll unhighlight that. This can be 1 or 4. Or 5, 6, 8, 9. I think we definitely have jellyfish on the 8 and 9 as well. So we'll get there. I just want to pencil all of these. I need 1, 2, 3. This can't be 2. 4, 5 are taken. I need 6, 8, 9. That's not an 8 either. Here I need 1, 3, 4, 6, 9. Okay. Here I need 2, 3, 8, 9. Here I need 2, 3, 4, 6, 8, 9. This is crazy. Here I need 2, 4, 5, 6, 8, 9. Not a 9. And then here I need 1, 2, 3, not 3. We need 4, 6. We need 8. Oh, there can't be an 8 either. Okay. So I baked in the 7 jellyfish now. And so now we have a jellyfish on 8s as well, except they're just here. This is where my 8 jellyfish is. Right? So this is where 8 can be in these columns, and so then these rows can't be 8 anymore. You can see I've already penciled a lot of them, which is nice. That's why I wanted to pencil all of these. So these blue cells can't be 8 anymore. So I'll get rid of the green, and I'll get rid of any blues that aren't interesting because they already couldn't be 8. This one as well couldn't be 8. So we can remove 8 from here and clear out the blue. We can remove 8. Actually, let's just remove 8 from all the blue cells that already have 8 marked. And then we just need to mark these as non-8. So this one can be 1. It can't be 2, 3. Can't be 4 actually because of the row. Could be 5, 6. Can't be 7 or 8. Could be 9. Okay. These could be 1, 2. That's not a 2. 4. We need 5. It's not a 5. We need 6 and 9. Okay. Get rid of that blue. This one could be 2, 4, 5, not 5, 6, 9. Okay, and this one can be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so only 1, 2, 3, 4. And finally, we have a jellyfish on 9s, which are here. This is where 9 can be in these columns, because we have this given 9 here. In fact, this can't be a 9, but we're not worried about that. So these are all blue. And none of these blue cells can be 9. They're all penciled, luckily. So this one's a 6. This one's a 1. This one's not 1, 6, or 9. Places the 1 in this box here. So we don't have to worry about that one. This one already couldn't be 9. This one can't be 9 and is not penciled. So 1, 2, could be 3, can't be 4, could be 5, could be 6. Oh, can't be 6, actually. Can't be 7, 8, or 9. Okay. Down here, not 6 or 9, not 9, not 9. That one's not 9, that one's not 9. Not 6 or 9. Okay. This one's not a 1, so we can place the 1 in this box. And then we can place the 3 in this box, which places the 1 in the 4. That places the 1 in this box. We get a deep, deep dude in the corner. I'm going to get rid of all the blue. That's not a 3 anymore. I almost removed the wrong digit. Okay. And I think from here we can probably solve it. So this is 1, 2, 3, 4, 5. Do watch. At the end, I'm going to look for something else. Another way to look at this, which might be interesting to you. So normally you skip the end of the solve after finding the technique. At least skip to after I've solved it and I want to show something cool. So, but you'll have to wait till the end. I want to make sure this solves. So we do need a 2 and a 3 in this column. They have to go here because of this 2, 3 out of here. And then this sees the 3. So this is the 2 and this is the 3. Oh, no, we don't need a 2 and a 3 in a column. We do need a 2 in the column, which goes here. I messed that up. Okay. I need a, let's see, what do I actually need? I need 2, 7, 8, 9. That's what I need. Oof. Okay. Do we have a jellyfish? We have a jellyfish here too, but so here's the thing with jellyfishes. There's always, just like how there's a naked triple versus hidden triple, right? That end up adding to 9, or sorry, a hidden and a naked that add up to the number of open cells left in the row or column or box. Just like that, if you find a fish of size n, so like a swordfish would be 3, a jellyfish would be 4, on, say, rows, then there will be an equivalent fish on columns, which is 9 minus n minus however many of those columns could already not be that digit. So, just to demonstrate, we had this jellyfish on 8s. So that's n equals 4, right? We had this n equals 4. For the columns. If we look at the rows instead, what we should expect to find is another jellyfish, because there is a singular there's a singular 8 in the grid. So that makes the fish add to 8. So if we find a 4 fish, a jellyfish, then there's going to be another 4 fish in the other direction. So instead of looking at the columns, I could look at these rows, and in these rows I have the same exact thing happening, where I get a jellyfish this way. Now here's the thing, they always eliminate the exact same digits. So even though there is always an equivalent fish the other way, it has the exact same eliminations, so there's no need to find it. And so what that means is you never, in a 9x9 Sudoku, for typical basic fish that go on rows and columns, you never need something bigger than a jellyfish, because let's say you find a 5 fish or a 6 fish or a 7 fish, there's going to be an equivalent 4 or less fish if you just look at the rows instead of columns or columns instead of rows. So that's why we don't have anything named beyond jellyfish until you start getting into esoteric fishes. So another interesting fact for you while I am not solving this puzzle. Let's see, what else are we doing here? There's a 6 in one of these two. Which means there's a 6 in one of these two. I feel like I don't know, I did scan this puzzle. How about this row? What do we need in this row? We have 1, 2, we do need a 3. We have 4, 5, 6. We need 7, 8, 9. We're going to need a lot of 7, 8, 9s. I wonder if there's something fundamental about how these fish overlapped that I didn't account for. But anyway, What am I doing here? This column, maybe? I'm not sure I like this column. Three's one of these two. Oh, fives I can mark now. Five's one of these two. Now that I have that one. For what it's worth. The two, not really that exciting. All right, I guess I have to start looking at some of these rows and columns that have 5 left. Let's look at this one. Maybe we'll look at the ones involved in the jellyfish. So 1, 2, 3, 4. We need 5. Oopsie. We need 5, 6, 7, 8, 9. That's not 6 or 8. These both aren't 7. That's not 9 or 5. Here we have 1. We need 2. We have 3, 4, 5. We need 6, 7, 8, 9. It's not 2 or 8. That's not a 6 because of the box. It's not a 9. That's not a 7. It's getting very cluttered. I was kind of hoping these would be the limited ones. Here I have 1. We need 2, 3. We have 4, 5, 6. We need 7, 8, 9. Not 3, 9. Not 3, 7. Not 2, 8. This box is not helping me. And I did this row. We could do these columns. It's almost all the cells in the grid are involved in these jellyfish columns and rows. So I've got 1, 2. I need 3. We've got 4, 5, 6 is down here. We need 7, 8, 9. Is there really nothing going on here? Here I've got 1, 2. I need 3, 4. We have 5, 6. We need 7, 8, 9. Ooh, this one's nice. It's not 3, 4, or 7. Okay. Just gotta kind of pick out the good cells, I guess. I bet there's something easier that I've completely missed, but let's just keep going. I need 2, 6, 7, 8, 9 here. That's not 2, 7. That's not 2, 6. Ooh, 9, 8, 6. I'm liking what's happening here. 3. We know 2's over here. Okay, well, we'll do this one. I need a 2. I've got 1, 3, 4, 6. So I need 2, 5, 7, 8, 9. 2, 7, 7, 5, 9, 5, 8, 9, 2, 7. I've got a 2, 7, 8 triple here. I guess that's what I needed. So this is the 3 and this is the 4 in the box. I probably should have seen 3 and 4 as hidden there, but I'm not sure why I didn't. All right, that's a 4 and that's a 5. These are not 5s. I'm fully marked, which is nasty. 7, 8, 9 triple here. So 4 and 5 in this row are limited. I've got the 4 here and the 5 here. Those are things I should have seen in scanning, so I think I didn't properly scan enough. I don't know. That's not a 4. It's just too much marked up. My gosh. 2's in one of these two in the 2, 7, 9 triple, so that's not a 2. So that places a 2 there. I've got an 8, 9 pair here. That makes that 6 and 5. That makes this 5 and 3. That's not a 5. That's not a 6. At least this will clean up fast. That's 2, 3, 6. Okay. These are all not 2's, and that's not a 6. 8, 9 pair gives us the 7 and the 6. These aren't 7. These aren't 3. That's not 2, 3, 7. Okay. Yeah, 3 in this row goes here. That's an 8. That's not an 8. I've got a 2, 7 pair here. We can clean up the 3 and 8 here. All right. I have to find more, I guess. 2's in one of these two. In this box, that points down. That's a 6. That's a 4, because it can't be 2. That's 7. That's 9. That's 6. These aren't 9s. Oh, we can do all these. 2 and 7. That's 7. That's 9. We get the 2. We get the 8. We get the 3. Yeah, let's clean all this up. Yeah, up here. We get this, the 8, the 9, the 9. We get the 8 here. 7 and 6. 9, 7, 8. 9, 2, and 7. We get the 8, 7, 9, 8, 2, 8, 9, and we're done. All right. Yeah, I missed some hiddens that appeared out of nowhere. I'm not sure exactly how that happened. Maybe they were hiddens in rows the whole time and I just missed it. But cool. That was a definitely intentionally constructed 3 jellyfishes by Sam, which is neat. So I did promise I was going to look at something. So let's take a look. I want to see how this looks when we use set instead of looking at them as fishes. So let's clear everything out. Everything cleared out. Okay. Sorry, puzzle. And what I'm going to do is I'm going to highlight these 4 rows. Let's use green. What can we say about green? Well, green is 4 rows. So the green cells contain 4 of each of the digits 1 to 9. This is SET, which stands for set equivalence theory. So it's a recursive acronym. But anyway, I think coined by Philip Newman. So green is exactly 1 to 9 4 times. We don't know exactly where they go, but we know green is that. Now what I'm going to do is I'm going to highlight 5 columns here in purple. What can we say about purple? Purple is 5 sets of the digits 1 to 9. Because it's 5 columns. That's what Sudoku tells us. Now, whatever digit ends up here, notice it is colored purple and green. So I could use the Scrabble bags analogy that Simon does on Cracking the Cryptic. But if I have a bag of tiles that are 4 of each of 1 to 9 in my left hand, and in my right hand, without hitting my microphone, I've got a bag of tiles where I have 5 of each of 1 to 9. My left hand is the green bag and my right hand is the purple bag. If I go into that bag and whatever this digit ends up being, if I take that tile out of the green bag and I take that tile out of the purple bag, my 2 bags have preserved an equivalence, which is that purple has every tile of green plus another 1 to 9. That was true to start with, and by removing the same digit tile from both, it's still true. And no matter how many I remove from both, as long as there's still one in each bag, I can keep removing them. And I've preserved the property that all of the tiles in green are in purple, plus purple has an extra 1 to 9. So I can just remove all of these from both colors, just make them white. And what I have learned here is that purple is exactly the green digits plus an extra 1 to 9. So now what I can do is I can go further. I can take a 2 out of each of these, still preserve that. I can take a 4 out of each of these. I can take a 3 out of each of these. I can take a 5 out of each of these. I can take a 5 out of them again. And there we go. What's interesting is we know exactly what's in green. Green has exactly 4 1s in it. Green has exactly a singular 2 in it. So when we translate that to purple, if green has 4 1s, because purple is all of the green digits plus an extra 1 to 9, that means purple has 5 1s in it. So the 1 has to go, like if we look at these columns here, it's 5 columns and 5 rows, right? The 1 is going to end up somewhere in there. So for example, one thing we could say is that we know there's a 1 in one of these 2. So these can't be 1, right? These can't be 1, sorry, and therefore there's a 1 in one of these 2. These can't be 1, right? So we can try to account for all these digits in these cells. Now, what I want to do is say that, okay, yeah, here's what we can do. How many 7s, 8s, and 9s are in green? Well, the answer is 0. There are no 7, 8s, or 9s in greens. Which means that this 7, 8, and 9 are the extra. These are the extra. So am I allowed to put another 7, 8, or 9 in purple? The answer is no. I am not allowed to put another 7, 8, or 9 in purple. Because otherwise, I would need to have one in green. Purple's only allowed to have 1 extra of each digit. In fact, it has exactly 1 extra of each digit. These are our extras. So none of the other purple cells can be 7, 8, or 9. So what I can do is I can go to every single purple cell and I can write 1 through 6 in them. Oops, I accidentally hit 9. And then I could clean it up, of course. That makes this gets our naked 6 here that we got. This gets a naked 1 up here. This makes this a 4, 5, right? We can just clean this up. I'm just trusting our red digits here, of course. Oops. 1, 3, 1, 3, 5, 1, 5, 6, 3, 5, 6. And then we can solve the puzzle from here. And this gets the same eliminations that we got from doing our 3 jellyfishes individually. So I thought that was pretty neat. You may even be able to figure out more that's going on here, like if you pay attention to how we need 5 ones. So for example, I need, okay, purple needs 5 ones, right? That means every single one of these rows can only have a 1 in purple. So where's 1 in this row? It's only here, right? 1 in this row is in one of these two. 1 in this row, it's here. That makes this a 3. That makes that a 1. So we could just count for every digit. We know that every single one of these rows needs a 2 in purple. Oh, sorry. No, we accounted for all these ones. So we can remove these ones and we can remove these ones. 1, 2, 3, 4. We've removed that. And this is our bonus 1 right here. So now 2s in purple. How many 2s are in green? There's 1 2 in green, so we only need 2 2s in purple. We should have exactly 2 2s in purple. So we can't do much about that. 3s, we have a single 3 in green, so we need 2 3s in purple. I don't see a way to limit it to only. Sorry, we need 2 3s in purple. We need 3 4s in purple. And I can actually get rid of these 6s. I can get rid of these 3s if I want. That should, oops, I'm not in color mode. Okay, I can get rid of these 6s. I can get rid of these 3s. Ideally, what I end up with is just 1 of each left, of each digit in purple, and that's the bonus ones. So 4, I need 3 4s. So I can count, I can make 1 of these a 4. I can make this a 4, and I can make 1 of these a 4. So that's our 4s. Those are the 3 4s. So this has to be a 4 for the column, right? Because I can split that up by columns. So that's not a 4. And now I can get rid of these 2 4s. And so I still need 2 more 4s. This column's going to need a 4 now. That's going to go there. So that's not a 4. So I can get rid of these 2 4s. Oops, I meant to just do that. Okay. So I've got my bonus. My bonus 4 actually ends up right here or here. We don't know where it goes. I do need 2 5s to go in purple. So let's count for where those go. They're going to end up in these 2 rows. So this is going to be a 5. And I can get rid of those colors. And then 5 is going to be one of those 2. And then I do need 2 6s in purple. These can be 6. So I don't think I can do anything with 6s right now. Because I can easily put like 4 6s in purple, so I can't limit that. So the 2 and the 6 we haven't accounted for yet. Now, after I place some of these, is the 2 or the 6 now limited? I don't see it. Okay, so from here, I think we could just easily solve the puzzle because of how much we've managed to get out of this set. And you could keep these purples around and the greens around just to, once you start doing more eliminations, find what to do. But should I try to solve from here? I may as well. I mean, it feels like we're pretty close to done. So I'm trying to remember like what the key cells were so I can save some time, but I'm not remembering very well. Yeah, I'm not seeing it. You can do some cool things like, I don't think the 2s do it. 6s. We know that there are 2 6s in these cells. I wonder if there's something cool we can do with that. Oh, wait, hold on. No, 6s are also here. There's 2 6s in these cells. So like one thing we could say, which isn't useful, is even if we were to put one of the 6s here, we'd still need a 6 in one of these, and they all see this cell. So this cell wouldn't be able to be a 6, but it already couldn't be, so that's not useful. Maybe I'll just scan. I don't know. 2s, look into here. So 2s in one of these 2. 3s, look into here. So 3s in one of these 2. I feel like there were like hiddens in these rows and columns that I had missed last time. But maybe that's what I got with filling out the purple cells. What can I do here? This box has 4 left. We need a 2. No, we don't need a 2. 1, 2, 3. We need 4. 4 is placed in this box. These 2 4s look down. Okay. So 4 is placed. I need a 6, 7, 9. So the 6 is over here. Yeah, 6, 7, 9. Clean that up. This box has 4 left. I need a 2, 3. Actually, the 2's in one of these two, so that's important. So in this box, this 2 looks in, so 2's in one of these two. That looks up, that places this 2. So now I can get rid of this. So now we just need the bonus 2. We need to find the bonus 2. And we also still need 2 6's. And that was one of the places 6 could be. So actually, I can cover 6 with this row and with this box, or with this column if you prefer. So that means that 6 is definitely one of these two and definitely one of these two. So I can mark 6's here. That puts this 6 here. 2, we don't know where that's going to end up, our bonus 2. Let's see, what else can we do here? This row needs, we have 1, 2, we need a 3, 4, 5, 6, we need 7, 8, 9. 3, 9, 7, 9. What do we still need in purple? That's an interesting question to ask. We have 1, so we need 2, 3, 4, 5, 6, and we need 2 6's. 2, 3, 4, 5, 6. 5? 5 can only go one place in purple, so this has to be a 5. That's a 3. So we now have a bonus 5 in purple. 2, 3, 4, 6. Okay, 4 can only go here in purple. That places this 6. That's our final non-bonus. So now we can treat purple as like a disjoint group, as like needing one of each digit. And actually it is a 2, 3, 6 triple already, so we've gotten what we needed out of purple. This is going to be, let's see, it can't be 1, 2, 3, 4, so we need a 5. If the 5 is placed here, we have the 6, we need 7, 8, and 9 that go here. Okay. This row, we have 1, 2, 3, 4, 5, 6, so we need 8 and 9 in this row. I don't even know if this is faster, but it's interesting. And then here in this box, oh no, sorry, not this. I wanted to do here 2, 3, 7, 8. These aren't 3's. Okay, so this 3 looks down, so this has to be the 3. That's not a 3. We have a 7, 8 pair here now. What do I want to do here? How about this triple? We need 2, 7, 9. 2, 7, 9. That's not a 2. Here, this triple is 2, 3, 8. So 3 in this row has to go here. Yep. That's a 7, 8, 9. So what is this? This is a 4. This box needs 7, 8, 9. Okay. This box needs a 7, 8, 9. That's not 8, that's not 9, that's not 7. This box needs a 2, 7, 8. So the 2's one of these. I remember having that last time. Maybe this column. This column has 1. We need 2, 6, 8. Oops. I'm in quarter mark mode. 2, 6, 8, 9. I'm still like resorting to, okay, 7, 8, 9 triple here. It puts the 6 and the 5 there. That puts the 2, 3, and 6. And now we have all our bonus digits in purple. So this is where the bonus digits ended up, at least the way I picked them. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 in purple. Those are the leftovers after we drained all of green and the equivalent digits from the purple bag. We have now been left with the extra 1 to 9 that was in the extra column from purple. So there we go. 1, 2, 3, 4, 5. We need 6 and 7 here. Those are placed. We get the 8 and the 7 here, the 2 and the 7, the 9, 2, and 8. That's the 8, that's the 9, that's 9 and 7. That's 7, 8, and 9. This is 2 and 7, that's 8, 7, and 9. And here we need a 3, and we need a 9. We get the 8 and the 9 here. We need 2 and 8 here. And this digit's an 8. And that time's wrong because it paused it as soon as I won last time. But yeah, so you can see that it did logically solve the puzzle. And so we could use that set for almost the entire solve to really, really, really reduce our options. And it really pointed out the consequence, not just of each individual jellyfish, but the fact that there were 3 jellyfishes that all used the same set, or a similar set, right? And we could do that unbalanced set. And when you're looking at stuff like this, where givens are like really clustered like this, that's the reason I knew exactly what set to use is, and we could have done it rows against column, or we could have rotated that 90 and gotten a very similar logic out of it. But the reason, what I wanted to do is I wanted to capture in as few rows or columns as possible. I wanted to capture these. So let's get rid of the purple. This is how I looked at it. Should I clear the puzzle again? I won't clear the puzzle again. But this is how I looked at it. So I said, I want to cover all of these crazy groupings of givens. I want to cover them in as few rows or columns as possible. And I chose rows, I believe. I don't even remember. I chose to use the rows here in these greens. And then the next goal is to use different styles of houses. Sometimes you might use boxes. Sometimes you might use columns. You can mix it around. Like you might experiment with doing these 3 boxes. In fact, with these 3 boxes, so the problem with using these 3 boxes is we don't have a good way of dealing with these, right? So I chose the columns because what I want to do is I want to get rid of anything that's not a given. I want to get rid of as many non-givens as I can. So if I choose this column and this column and this column and this column, I'm basically covering as many, and this column, I'm covering as many non-givens as I can while avoiding covering givens with my other set, right? With my purple. Because then the overlap between the purple and the green are going to go away on their own. Right? And what we're left with is green being completely full of givens. So we know exactly what goes in purple, which is amazing. We know that purple has exactly all of these green digits. Plus, because I did an unbalanced set, I did 5 columns versus 4 rows. It also has 1 to 9 in addition to that. So that is how I immediately knew what set to use. And I think I could have also, it's going to tell me I won again. I've realized what happens is if you press delete at any point in time after you've solved the puzzle, it brings the dialog again. Anyway, so instead of covering them with the rows, I could have done green as these 4 columns, and then I could have done these 5 rows. But you'll notice something interesting happens here. I believe I should still end up with the same set. It's exactly the same set, right? So if you do it this way, you still end up with an unbalanced set where green is in purple. It's the same exact cells. So anyway, yeah, I hope you enjoyed that. You may have encountered set before in the form of the Fistamethel ring, if anything. But it's not limited to just the Fistamethel ring. There are all kinds of things you can do with set. But the trick is doing it in a way that's actually helpful. And I knew for sure this would be helpful just because we had those 3 jellyfishes that used the same set of givens to restrict them. So I was like, this is gonna be viewable with set. So anyway, hope you enjoyed that. Hope you enjoyed this sort of extra set lesson at the end there. And of course, if you did enjoy it, why not leave a like, subscribe, and a kind comment below.